So this is Real Analysis. My name is Chris Stecker. That's how you say my last name. If you're interested in saying it, that's how you say it. Let's talk about the syllabus a little bit, and then we can get down to some business. So my email address is on there. That's the best way to get in touch with me. I also put my office phone number. Nobody ever calls my office phone, but you can if you want to. I might answer it. My office is Bano number 16, which is right next to Professor Rafalski in that area in the basement there. My office hours are there: Tuesday, Friday, 10 to 11, and Wednesday, 1:30 to 3. Those are times when I definitely will be there, just waiting for you to come and talk to me. But if that's not good for you, then I'd be happy to make some other arrangements. Before class on Wednesday is really the bulk of that time, and our homework assignments will always be due on Wednesdays. So homework's due on Wednesday, and my office hours include the 90 minutes before this class on Wednesday. So hopefully that will be a convenient time for you all. It says all the office hours are going to be in my office or on Zoom. So I will be sitting down there waiting for you to show up. And I'll also have my Zoom turned on my computer, so you can just come that way if you prefer that. The textbook, I forgot to bring it. I was going to show it off to everybody, but the textbook is called Understanding Analysis. The second edition, there is a first edition in there. They're quite different, so you need to get the second edition. We're really, for the most part, only going to use it for the homework assignments, so you don't need to bring it to class. And I'm not condoning it, but you might be able to find a copy online from some shady websites, and that will probably do okay for you just to get the homework assignments. Although you might find it helpful to read the book, but if you want to go that way, you may do okay like that. The final exam time is there, December 20th at 3 p.m. Be there. And the class website, you can hit this thing and go to the website that you'll want to visit, because that's where I'm going to post the homework assignments. So you will want to check that out at least once a week. I am also, I hope it's all right that I'm going to write everything on the screen here. I am doing that because I'm going to record everything that I'm doing as a video. I don't have like a camera on me, but just the video of me writing, and you'll be able to hear me. And I'm going to post those on YouTube after the fact, so you can check them out that way. And you'll see links to those videos on the website. So if you have to miss class or whatever, it should be fairly easy to keep up. And I'm also, what I'm writing on here is I will turn into a PDF, and then I'm going to post that also, so you should be able to read my notes. So hopefully that will be helpful. Check it out on the class website. Be sure to like and subscribe. Ring that bell. You don't need to ring the bell. All right. Let's talk about the course content. This is what it says on the official description of this class. This course examines the set of real numbers as a complete ordered Archimedean field. R as a linear vector space equipped with inner product and norm. Metrics, particularly Euclidean on R topological concepts, continuity, connectedness, and compactness. Intermediate value, extreme value, monotone convergence, Bolzano-Weierstrass and Heidenberg theorems. Convergence and uniform convergence of sequences of continuous functions, and differentiation, maybe. There's a lot of topics in this class, and I don't expect you really to know what any of those words mean. Maybe some of them look familiar, but this is a typical real analysis class. If I were to describe in vague terms what the class is about, I would say it's about the same things that calculus is about, but it's done at on a more theoretical level. So it is basically about the same stuff that you talk about in a calculus class, but day to day, what we do in class and what you do on the homeworks is nothing like a calculus class, which calculus class is kind of like you learn some rule and then you do 50 problems doing the product rule over and over again or something like that. And this is nothing like that. But it is about the same concepts that are from calculus. Most of today I'm just going to try and give you some kind of a historical overview to give you a sense of where we're going with all this. But that's what the class is about. It's kind of technical, and there will be a lot of writing proofs of things, which you usually don't do more or less at all in a calculus class. But it's very interesting material, in my opinion. I'll try and convince you, today that it is interesting to talk about. Anyway, let's just talk about the rest of the syllabus here. There's going to be 2 exams during class. That we're just going to, instead of class one day, we'll just do a test instead. October 14th and November 18th, those are 2 Fridays. Be there. It says no calculators on the test. This is not that kind of class. Your calculator would not do you any good, so no calculators. There will be a final exam. It says the final exam will be cumulative, but the midterm exams will not be. So that's that. The homework will be due roughly once per week on Wednesday. The homeworks, no homework due tomorrow, but typically after each week of class, so the sort of Tuesday through Friday, all of that material will appear on the homework that's due on the next Wednesday. So you'll have the weekend plus a few extra days to do the homework. Like I said, I'm going to have office hours every Wednesday before class, so hopefully that's convenient. But if not, I'm happy to talk about it some other time. The homework is going to be collected on Gradescope. Most of you used this before. You should have gotten an email earlier today, this morning, with information about your account on Gradescope. I just learned that Gradescope now has an app. You don't have to use the website anymore, which I don't know if that is any good, but you might want to check that out. So that's the homework. Assignments will be posted at the class website, and there will be problems from the textbook. So you'll want to get the book fairly soon, I guess, to do the, we probably will have a homework assignment due next week. All right? Online submission, like I said, is going to be on Gradescope, and that's really it. Some classes we have quizzes, but because of the nature of the kinds of things that we're doing, they're not really very conducive to having sort of like a 5-minute quiz question about this or that. So it's just going to be homeworks and exams, and you can see the grading ratios there. Homework 65, exams 35. All right? And just a little note about my office hours. This is just to say, I hope that you will feel free to talk to me about the homeworks or about the tests or whatever else during my office hours. I consider it to be a normal part of the learning process for everybody, not just people who are doing badly, but everybody, I think, is part of the process is to talk with other people, and that could be me. You don't have to talk to me ever if you don't want to, but I hope that you will feel free to ask questions from time to time. All right? That's about it. Anybody have any questions about that? I think no gimmicks really. Just do the homeworks and do the tests. That's all you got to do. All right. I know sometimes it's nice to have gimmicks, but not this time. All right. Let's talk about real analysis then. Please feel free to interrupt me as I'm rambling on. Like I said, everything that I write here, I'm gonna post later on. I know some people feel like it's easier to concentrate if you're not trying to take notes all the time. To me, it helps me constantly try to take notes, but however you wanna play it is fine with me. So this class is about the real numbers. That's why the word real analysis, because it's about the real numbers. Is about the real numbers, which I'm going to write like that fancy looking R thing. And specifically, it's going to mostly be about ideas from calculus. Some people ask me, actually, like in my ordinary life, when I meet somebody at the club or whatever, and I tell them I'm a math professor. Sometimes people always ask me, well, what do you teach? and I usually say, well, like a typical semester, I teach some kind of calculus and then something else. Because so many people have to take calculus, usually we end up teaching some calculus and something else. And sometimes people say, you know, I've heard of calculus, but I don't even know what that, like, what is calculus? What is it really about? And to someone who's taken a calculus class, I would say, well, it's kind of about like doing the derivative and the integral over and over again. That's like what it feels like, at least when you're in a calculus class. But that's not a good example. That's not a good answer to somebody who really doesn't know what any of that is about. So usually I say something like calculus is about how things change, or it's about like a mathematical study of something which is changing from moment to moment or over time or something like that. And that's why like everybody cares about that. Like it's important in physics or in business or like anytime you want to study something which is changing over time, calculus might be helpful in that kind of thing. But anyway, what a calculus class, I would say mostly is about the derivative and the integral. That's what you usually think of your class being about. But both of those ideas are actually based on a single, more fundamental concept. Anybody know what I'm thinking of? There's like one idea which, I don't know if you ever thought of it this way, but actually is at the heart of everything you do in calculus. It's part of, say, the definition of the derivative and also part of the definition of the integral. You know what I'm thinking of? It's usually something you talk about like for maybe a couple weeks at the beginning of a calculus class, and then you get into what feels like the real material afterwards. Yeah? Limits, yeah. Actually, it's a common thing for like mathematicians speaking to other well-versed people to say the fundamental idea of calculus is the idea of a limit. This is a common thing that mathematicians would say, even though a typical calculus student feels like, oh, that was just that thing we did for like 1 week and then we started the real stuff. But from a theoretical point of view, the limit is the fundamental idea which enables you to talk about the derivative. As the derivative is the limit of tangent lines or whatever. And it also enables you to talk about the integral as a limit of Riemann sums. So I will say the fundamental idea in calculus, even though it might not feel this way in a calculus class, but it really is. The fundamental idea of calculus from an abstract point of view is the limit. And I'm here to tell you, I don't know if you noticed this at the time, but when you learned calculus, you likely did not actually talk very specifically about what the limit actually means. For example, when I say this, I learned a little bit about limits when I was in high school. I wasn't any kind of math prodigy when I was a kid, but I remember learning about this kind of thing even when I was in high school. Limit as x approaches 3 of f of x equals 5. How my high school teacher explained this to me, and you probably heard something similar, was what does that mean when you see this? What does that tell you about the function? Here's what it means. It means when x gets really, really close to 3, then the y value, f of x, gets really close to 5. All right? That, what I just said, is kind of nonsense. And I don't know if it ever occurred to you before, but that, what I just said, is not a legitimate definition. So this is often discussed in terms of really, really close. They say really twice. Really, really close. The double really should be a hint that there's some kind of funny business at work here. When x is really close to 3, I don't know if you ever thought about this, but then f of x is close. They might say really, really close. They're feeling excited about it. I don't know if you ever thought about this. This, as a definition, is unlike anything you've ever seen in other mathematical contexts. Like, when you say when x is close to 3, the appropriate and natural sort of mathematical response to that x is close to 3 would be, how close do you mean to 3? Now, you should really, in your mind, be thinking of this picture, right? This is what this picture means, right? It means as I travel along the curve, when the x goes to the 3, the y value goes to the 5, right? That's what you should be thinking of. But when I say it this way, when the x is close to 3, well, how close do you mean? Like, you mean like within 1 of 3? I would say actually 1 is kind of far away from, I don't know, I mean like really close. Well, how, like within 0.01? I guess so, but even if you zoomed in, like really, really, really close. Really, what you mean by really, really close is kind of non-specific. Like you don't actually mean any particular distance away from 3. You mean kind of something else, right? Like really, really close. What does that mean at all, though? And then what does this mean? F of x is really close to 5. From another way you could think of this, well, x is a number, right? Yeah, x is a number. So how can a number, sometimes people say, all right, forget about really, really close. How about as x approaches 3, then f of x approaches 5? I have similar issues with the word approach because x is supposed to be a number. A number doesn't approach anything, right? A number doesn't approach 3. It is 3 or it is not 3, but there's some kind of, somebody who says this is trying to make me think of x as being like a thing which moves, or something like that. But a number is not a thing which moves. If x is not supposed to be a number, then what is it? All of these are kind of, like the purpose of this, saying these words to a high school student, is to make them feel like they understand what you're talking about so that you can get on to the derivative, something else, right? Because for the rest of the calculus class, you don't even really think about exactly what these words are supposed to mean. This is kind of like, saying, you know, when a mommy and a daddy love each other very much, that's where a baby comes from. Like, when you say that, you are trying to get the kid to feel like they understood what you're talking about and then move on without really dwelling on the explicit details of what you're really talking about but trying to avoid, right? This is how we do it in a typical calculus class. This right here, so this idea of limit is kind of the mommy and a daddy love each other very much version of the definition of a limit. There is a real definition in which everything completely makes sense, which involves no something really close or something approaching or any of that. Those are all kind of wishy-washy sort of intuition-building words, which are not really, they don't really count as real definitions. So that's going to be kind of the centerpiece of this course. We're not going to get to the real definition today, but that's sort of where these ideas are building towards. You know, I said this class is basically the same ideas from calculus, but done at a more in a more abstract way, or something like that. Really, what this is the ideas from calculus, but done in a correct way, like in a way which doesn't involve bogus definitions like this here. Right? We're going to have actual, real definitions for everything, as much as possible, at least. So that's where we're going. I thought what I want to talk about today is mostly, I want to talk about some kind of, maybe a little review of the history. I don't know if you guys are interested in the history of these ideas. I think there's an especially interesting history of ideas about real analysis. So a strange and complicated history. So I would say this perhaps begins, I'm going to say it begins in the late 1600s when Newton and Leibniz invented calculus. I'll put that in quotes because of what I'm about to say, but this is what, you know, most people will tell you if you ask who invented calculus. It was Isaac Newton and Leibniz, who is a German mathematician. They more or less came up with the same idea at the same time, but not doing it together. And then they actually had a big feud between them about who should be given the real credit for inventing calculus. They did it very differently than we do today, and actually a lot of the notations that we have for things are different because of this two separate inventions. Like Newton wrote things like this, and Leibniz wrote things like this, and we still write things in those two different ways to mean the same thing. But and they also had different terminology for everything that we use. Newton called the derivative. Newton called, or like the whole subject. Newton referred to it as the study of fluxions, which we don't use that word anymore. But yeah. Somebody else came up with the word derivative. Anyway, what's important for our purposes is Newton and Leibniz, they invented calculus, but never defined limit. They would have said things like something gets really, really close to something else, or something like that. All right? But to them, it wasn't something they were focused on. I think at this time in history, there wasn't like the discipline of pure abstract mathematics didn't really exist. You know, Newton and Leibniz were both inventing calculus in order to solve physics problems. And they came up with things like the product rule or whatever, which gave the correct answers for physics problems. And that's really what they cared about. And they didn't focus on making real like definitions that I would approve of. That just wasn't what they were interested in doing. So they didn't. And this situation persisted for a long time, where there was nobody ever really thought about, hey, what do you really mean by limit in a specific way? What exactly do you mean when you say something gets really close to something else? Until in the 1810s, a guy named Bolzano, you saw his name in the syllabus. He's one of the big names in the early real analysis. Bolzano published a real definition, actual definition of limit that would be like recognizably the same as the way that we think of the real definition of a limit today. The same definition, but nobody cared. Today, we regard this as a major advance in real analysis, and really, maybe you could say the proper birth of real, like actual real analysis, and not just trying to do calculus to get answers to some specific problems, which of course is super important. But as a mathematical discipline, this is kind of like the birth of actual real analysis. But at the time, nobody recognized it as significant. I think just because culturally, people still didn't really care about real definitions for things. They were using calculus as a tool to solve other problems. And if you're doing that, you don't really need the real definition. And so this was not regarded as important by anyone. Then, in the 1820s, Cauchy, you may have heard of, this is another big name. Bolzano was kind of obscure. Nobody knew Bolzano anyway. So he wrote this paper, and they were like, who's that guy? And I don't care anyway. And it didn't go anywhere. Cauchy is a big name. Cauchy came up with the same thing, not copying from Bolzano, but just like on his own. But even so, nobody cared. Even though Cauchy was a big deal on the scene, still it was not, somehow the culture was not ready to appreciate how important this was. And then in the 1850s, this guy, Weierstrass, who's also in the, sorry, I gotta spell it right, this way. Also a name in the syllabus, Weierstrass, again came up with the same definition, and this time everybody loved it. So for some reason the culture had changed enough that same thing, and this time it was regarded as a major breakthrough. And so there are many things which have Weierstrass's name on them that maybe should have been attributed to Bolzano. Like in the syllabus is something called the Bolzano-Weierstrass theorem. They did not know each other and work together on this. It was just Bolzano did it and nobody cared, and then Weierstrass did the same thing and everyone was like, oh, this is amazing. So Weierstrass, same thing, but I will say very well received. And people sort of realize at that time that, oh, okay, everything we've ever been doing in calculus for the past 200 years is actually about this. We didn't even know what, on some sense, we didn't even know what we were talking about until now, and now we do. And everybody sort of the foundations of calculus were completely rewritten based on what Weierstrass had done, even though it had already been done. Just nobody cared until then. All right. There's a cute quote about this by a math historian named I think it's Judy Rabiner. I'm not sure how you're supposed to say that, but this is a cute quote about this. She says, first the derivative. She's talking about the derivative in particular, but really you could say this about the limit, is what I'm talking about. First the derivative was used, then discovered, explored, and developed. And only then defined. It's a true fact. It's weird. This is true of many old disciplines in mathematics. Like 20th century math is not really like this, but before that, this is true in many cases that people were doing calculus and using calculus for hundreds of years before they had real definitions for anything that they were talking about. Strange but true fact about the history of real analysis. I think it's interesting. Any thoughts about that? Did you get any? No, of course not. I hope it's interesting. I got a little more history that will lead us more directly into what we are going to start our first topic. So let's talk about real numbers and rational numbers. Because even the concept of real numbers is kind of a recent historical development in the history of humanity. Human beings have been thinking about numbers for as long as they've been thinking about anything, I guess. The rational numbers have been around for a much longer time, though, than our concept of the real numbers. I think the concept of the real numbers is kind of a modern concept. But I'm going to give you like a 10-minute history of numbers throughout all of history. So let's start with the Pythagoreans. This is the Greeks, right? Around, say, 500 BC. They thought of, they had very sophisticated mathematics that they did. They had the Pythagorean theorem and lots of other things like that. They thought about everything in terms of geometry. Everything is geometric. All right? I think nowadays, when we think of it, like, I'll speak for myself. When I think of a number, say the number 5, what does number 5 mean to me? I usually think of it in terms of it represents a quantity of things, like 5 buckets or 5 apples or whatever. I think the Greeks were more inclined to think of everything as a distance. 5 is this many as opposed to this many, right? This long. So the Greeks, because all of their mathematics was based on geometry, probably not all, but this is the way that they thought of numbers in general. So everything is geometric and all measured, when talking about mathematics, all measured in abstract units. Like they loved things, everybody loves things like this, right? The 3, 4, 5 right triangle. They appreciated some kind of beautiful and even like spiritual relationship between the numbers 3, 4, and 5 because they can fit in a diagram like this. And those numbers are interesting for geometric reasons, all right? And they thought of these in terms of abstract units in the sense that they would draw pictures like this, not meaning like the 3 is specifically 3 miles or whatever, but it's just 3 whatevers, 3 abstract units. And they believed that all lengths should, well, they believe, I will say it this way, all numbers should be what they call commensurable. Commensurable means measurable in the same units. So in this picture, the hypotenuse of 5 is 5 units of the same units that are used over here. There's 3 over here, and 4 over here, and 5 over here. So commensurable sort of means expressible as integers of some units. Right? Or fractions. They were cool with fractions too, because like this picture they would have recognized as being somehow the same as like this picture, where I just divided all the lengths by 5, but it's really the same figure, and those distances are still all expressed not exactly as integer values of some units, but they might as well be integer values in some units. All right. This is why it was very strange when the Greeks discovered, and they made a big deal about this in their writings, when they discovered things like this. This thing here, they actually knew, the Greeks proved, they were able to prove things like this, that root 2 is not any ratio of the abstract unit. Like that side, which I don't know if they would have written it as a root 2 like we do, but they would have just said that third side there is not expressible in terms of the units at all, because it's not any ratio. Like we would say, square root of 2 is an irrational number. That's what it means. But they were very impressed by this fact and puzzled and disturbed by this. Our modern interpretation of this situation is just, well, some numbers are rational and some are irrational, and that one is irrational. The square root of 2 is not a rational number. The Greek interpretation of this, though, was not. They did not come to that conclusion. The Greeks, their conclusion here is basically, apparently, not all lengths are numbers. Like the standard Greek Pythagorean interpretation of this is just that hypotenuse there, it's not a number. Like it's something. You can draw that triangle if you want to, but that hypotenuse is not actually a number, because it's not expressible in terms of the units that the other sides are expressible as. All right. To our modern people would say, yeah, it is a number. It's just not like those other ones. But they didn't even think of that as a number. All right. So there was some much later development in this. So around the like 800s to 1000 AD now. This is the time when the Arab mathematicians were going crazy. There was a lot of work in India. Like India and China were major sort of centers, and then this sort of moved west to the Middle East for a time. The Arab interpretation was a little bit different. So they were very much influenced by the Greek writings, but the Arabs, their interpretation, they sort of decided that these things like root 2 are also numbers. And we can still, I'll say, we can do arithmetic with them. Like, if you want to, you can say add them together, or multiply them together, or divide them, or do that kind of stuff, which the Greeks would not have done that kind of stuff with them, because they didn't really consider them to be numbers. This all maybe seems kind of obvious to us, but I think of root 2 as a number because it's like I can do that on my calculator. It's like 1.4 something, right? And if you want to add root 2 plus 1, it's like 1.4 something plus 1 is 2.4 something. Right? That's easy for me to understand. But you got to think about at this time, they didn't even write numbers in decimal expansions. Like, there was no, I mean, I feel like when I write root 2, I also feel like I could get my calculator out and figure out, what is that really? It really is 1 point whatever. They didn't even think of that at all. Like, all it is root 2. And they could try to measure this distance to tell like exactly how long it is. But really, they were not thinking of it as a number. So this was a big change in point of view. Those other things, even though we might not know precisely what that value is, we should still think of it as a number, and we can still do arithmetic with them. So nowadays we consider the set of real numbers is another way to say that we can still do arithmetic with them. I would say the real numbers is a field. This is a word from abstract algebra. If you take in our abstract algebra class, you know about like what a group is. A group is a set where you can multiply the elements by one another. A field is a set where you can multiply and also add them. You have two different operations. They work together nicely. And what's also special about the real numbers, not only is it a field, there are many fields. A field is just any set, any abstract set which has an addition and also multiplication. But like other things like the set of all 2 by 2 matrices is also a field because you can add matrices and you can also multiply them. But also a field, and it's also ordered. This is why we think of the real numbers as a line. They go sort of one after each other. It is a field. It is also ordered, and this is the first thing that we're going to talk about as like a major topic. It's also ordered, and the fancy word for this is complete. And what this means is there are no, I would say, gaps, or there's no like missing stuff in between real numbers. Unlike, say, the integers are nice. You can add them and multiply them. They also go in order, but there's big gaps in between from one integer to the next. There's a lot of stuff missing in the middle. So I will say the z, that's the set of the integers, and q, that's the set of the rationals. So these are integers. This q is rationals. These are not complete. Why the z is not complete? That's obvious. The integers, that's just the whole numbers, and there's plenty of stuff in between the whole numbers. There are big gaps from one to the next. The rationals is a little less obvious, but it is also true that if you consider only the rational numbers, they don't really make a nice solid line, right? I can draw the real number line. If this is the real number line, I could also draw just the rational numbers, would be like some of those, but not all of them. And the rational numbers, it's kind of like a cloud of dust. There's just a bunch of individual rational numbers, but in between them, there's always some irrationals all over the place, right? So this little dust here would be how I indicate the rational numbers. Not all the real numbers are rational, and the ones which are irrational are kind of distributed all over the place. So that the rational numbers just by themselves don't actually fill up a complete line. That's what this word complete. The integers and the rationals are not complete. All right. And this is the unique fact about the real numbers. So the real numbers is actually the real numbers is the only complete ordered field this is a big theorem, which actually we're not going to talk about this because this is really a theorem about algebra. It says there are no other ways to make a complete ordered field other than the set of the real numbers. But this is an important, it's sort of a deep fact about what's so special about the real numbers. Why do people talk about the real numbers rather than only focusing all the time on the rationals? It's because the rationals are not complete, and there are some numbers that you want to consider to be actual numbers, but they're not rational, right? As the Greeks learned. All right. We got 10 minutes left. I think that's enough to talk about our first little baby theorem. Can you believe it? Maybe we'll do, I want to do the proof, maybe we'll leave the proof till next time. So the first big idea that we're going to talk about is completeness. That's the first sort of section of the class, is about the completeness property of the real numbers. Completeness is about little gaps, itty bitty missing numbers or something like that. And we're going to talk a lot about distances. Whenever I say something like really close or itty bitty, it's a fundamental idea in this class, is about distances between real numbers. So we're going to say a lot of things about distances between numbers, between real numbers. And so just something very simple, the distance from one number to another. So if I have two numbers, say x and y, the distance from x to y is, how would you actually find the distance? There's sort of a simple formula for this, which I'm sure you've used in other classes. When I write a formula, and you could write it something like this: d of xy, the distance from x to y. How would you find that out? This is not that complicated.
It's just y minus x.
Y minus x, yeah, almost. That would be if y is bigger than x, then you do y minus x. I want the answer to always be a positive number. So, yeah, how about the absolute value of y minus x? Which is, that's the same as the absolute value of x minus y, right? Absolute value. Uh-oh, low battery. We have 8 minutes. I had my laptop plugged in all day in my office, but then I realized sometime over the summer my power strip got unplugged, so it actually wasn't plugged in. Just thought I'd share with you that cute little story. This is going to be a big deal in this class, just to talk about distances. Unfortunately, that means we are going to talk a lot about absolute values. And absolute values, maybe it's just my upbringing, I hate dealing with absolute values. So my typical approach when I was a student, when I see the absolute value, I ignore the absolute value. That was always my approach, which is not always correct. So unfortunately, we will be dealing a lot with absolute values. Important fact about absolute values is the triangle inequality. It says the absolute value x plus y is less than or equal to absolute value of x plus absolute value of y. This is called the triangle inequality, and we're going to use this all the time. Why it's called the triangle inequality has to do with this property for distances in not in real numbers, but in say R2. This, you can draw a picture of this and it looks like a triangle. If this, say if I have two vectors, x and y, then this is the length of x, this is the length of y, and then this distance here is, sorry, not that. I mean this, the length of x plus y. If you think of these things as vectors, what it means to say the length of x plus y is less than the length of x plus the length of y, it means in a picture like that, I could redraw, say move this y as a vector over here, right? It would be that. And now because of this triangle and because the shortest distance between 2 points is the straight line, this distance going straight up the diagonal is less than these two distances added together. All right, that's why the distance or the length of x plus y is less than the length of x plus the length of y. If you draw all of this just in one dimension, then you get the same thing, but for the ordinary absolute value of real numbers. All right, this is a super important fact. We're going to use this all the time to work with inequalities involving absolute values, which is something that we're going to use all the time. All right, a second important fact, and then we'll which is also something that everybody's very familiar with. I will just say also, this is pretty obvious, I think. X is equal to y if and only if absolute value x minus y equals 0. That is, if the distance, this here is the distance, right? The distance from x to y. If the distance from x to y is 0, that means x and y are equal. They are the same number, right? This also is a obvious thing, but we're going to use that all the time. And now I would like to get into the spirit of real analysis, sort of a basic idea, which is very simple, but we're going to be using this same basic idea in ever increasingly complicated ways over the course of the semester. So this, I will call this is our first epsilon. That's a Greek letter epsilon, which will be used every day for the rest of the semester. Epsilon is used all the time in real analysis in a very particular way, which I will demonstrate in this first theorem here. I would like to do the proof of this theorem next time. It's not actually that hard, but just because I want to get us used to doing proofs of things in this class. The theorem is about when a number is 0. This is going to seem very simple. Here it is. I'll just write it. X equals 0 if and only if. This if with two f's means if and only if. It means, remember from your discrete math, it means the thing is equivalent to the other thing. This thing implies that thing, and also that thing implies the first thing. X equals 0 if and only if. Here we go. For any epsilon greater than 0, so epsilon is a real number which is greater than 0. Absolute value x is less than epsilon. So in our remaining 3 minutes, I don't want to do the proof of this. I just want to convince you all that this is actually true and make some sense of this. This is a little confusing. This part over here. For any epsilon greater than 0, the absolute value of x is less than epsilon. What does that tell you about the number x? Basically, what this says over here is x, when you take the absolute value, is smaller than epsilon. And that is true no matter what epsilon is, right? For any number, epsilon, x is always smaller than that. What is your conclusion? Well, then x must be 0. That's the only number which is smaller than every other number that's greater than 0, right? That's how you should interpret this. So what this says over here is kind of like absolute value x is smaller than any positive number, right? That's sort of what this means. For any number, epsilon greater than 0, the x is less than that epsilon.
Is there a reason why we use epsilon or any variable?
You could use any variable you want, but Weierstrass called it epsilon, and so we call it epsilon. Yeah. So you imagine this epsilon, I want to say, we imagine, this is like a very deep, I have 1 more minute, I will try to convince you that this is important. This is something that took decades for people to realize was important back in the day. We imagine that epsilon is super small, right? Because here I'm saying x is smaller than any number. You think of epsilon as being like a really itty-bitty number. That's the only case in which this is actually interesting, what I'm saying here. When epsilon is some super small number, x is always less than that. That means x has to be 0, right? But what I said here, I never actually said that epsilon is an itty-bitty number. You don't have to say that as part of this, okay? This kind of thing is how you say when something is really, really close, without saying really, really close. This is this kind of epsilon strategy here, and this is a very simple example. We're going to do it in more complicated examples, but this is the way that you talk about something really, really small without ever saying really, really small. You say, really the key phrase is right here. This we're going to say over and over again in all of our definitions and theorems. They will say something like this. And this is the magic phrase which lets you talk about something being really small without actually saying it. This is, in my opinion, that is the brilliance of Bolzano and Weierstrass and all those people, to say really small without actually saying it. So, a lot more like that in the future. That'll do it for today.